So, hello everybody. Welcome to today's class, which is going to be on complex numbers. But before we start off on complex numbers, I want to take up this doubt that Prajwal has sent. I thought it's an interesting doubt on limits, so it's useful for everybody. So I thought I'll just discuss it here instead of just sending him an explanation. Okay. So let us get started. And Itachi, today's full class is on geometry because complex numbers with geometry. So yes, today we'll be doing a lot of geometry. But let us go ahead and look at Prajwal's question. Everybody can see it, right? One second. Wait. This is. I need to get to this side of the screen. Wait. There's some problem. Just hold on. Wait a second. This is causing some trouble. Let me try this. Some slight issue. Just give me a second and I'll figure out what went wrong. Mess has happened here. I think I need a little. Just need 2 minutes. Usha ma'am, just give me like 2 minutes. I'll finish this and then I'll get started. There's some problem with my system. Okay, now I think my system is okay. Finally, just a minute. Let me see if I can get this working fully. Just hold on. I don't know. Some in computer systems always have problems, but this particular one, I don't know what is the issue. Anyway, let's see. Okay, so can everybody see me now? See my screen also? Yeah, you can see both, right? Usha ma'am, this is clear, right? No, you are on mute. Okay, fine. Right, so you don't need to be on mute, Usha ma'am, so that I'm anyway muting you from here. Okay, let's get started. So already we I wasted some time here. Let me get started here. Let's see this. Yeah. So this is Prajwal's question, right? So this is the question that he's been asking. He's asked. He wants to find the limit x square plus x plus 1 by x plus 1 minus ax minus b. That limit is given, it's 4. And what is done is x square is writing x square. Oops, what is something weird? Okay. X. What is wrong with my keypad, writing pad? Okay. Okay, this is. Looks like no, it's fine. Okay, let's see if it works or starts acting up. I think something is wrong with my writing pad. Just a second. Okay, no, it's better. Okay. So basically, I have got x square by x plus 1. And he's taken this x plus 1 and divided by x plus 1. And so he's got plus 1. Minus ax minus b. The problem with this is approximately x. This is approximately x. But what does that mean? It's approximately x. If x cancels out, then you cannot call it approximately x. Correct? So by calling it approximately x, you can say x minus ax. This is 1 minus b. Now this must cancel out, otherwise x is going to infinity. So a must be equal to 1. Till here it's not a problem. Not at all a problem. But the moment you say a equals 1, you know that this x is going to cancel out. So then it is not enough to write this as x. You have to go one step further. Okay. So a equals 1 is not a problem. A equals 1 will work. But the moment you say a is equal to 1, this cancels out. So you need one more approximation. So x square, let me write x square plus x minus x, okay, by x plus 1. I'm just writing this, rewriting this. I want a better approximation than x. I will do minus 1 plus 1. Now, if you notice, this part is x times x plus 1 by x plus 1. So this is x. This is what you had assumed, Prajwal. And then this part, right, it is minus of x plus 1 by x plus 1. So minus 1 plus 1 by x plus 1. Now this I can say is very small. So a better approximation is x minus 1. Is that wrong to say it is approximately x? No, it is not wrong. As long as x does not cancel out, but x is going to cancel out. So this is a better approximation. So if we use that now, x minus 1 minus, right, x minus 1 plus 1 here, minus ax. Now you already know a is 1, minus b. Now this limit is equal to 4. And so you can see that minus b is equal to 4 or b equals minus 4. You got b equals minus 3. Because your approximation said it was x. But that is only valid as long as x does not cancel. Another way of doing the same thing is to expand this out a little more. And you write x square plus x plus 1 minus ax square minus ax minus bx and minus b by x plus 1. Now if I look at this, this is 1 minus a times x square, 1 minus a times x square. And then if I look at this, this is 1 minus a minus b times x plus 1 minus b by x plus 1. Now, if a is not 1, the numerator will behave like something of the order of x square divided by x. So that means overall it will behave like something into x, which is going to go to infinity. So this has to be 0. So from this statement, I can find out a must be 1. Now, this whole thing, you want it to cancel out and become equal to 4. That means this term and this term, right? You want it to be 4, right? How do you make it 4? Substitute a equals 1. So first of all, this will cancel out. You're going to get minus bx plus 1 minus b by x plus 1 must behave like 4. So which means the numerator must behave like 4x plus 1. Sorry, 4x plus 4. So minus b plus 1 minus b must behave like 4x plus 4. How is that going to work? Unless minus b was 4, this won't work. No. But if minus b was 4, will my limit be 4? So minus b is 4 means b is equal to minus 4. But if I put b equals minus 4, this will become 5. Is that a problem? Actually, it's not a problem. Why is it not a problem? Because if b is minus 4, okay, when I look at it like this, these two are approximately equal. Approximately equal, but you want to divide. So the approximately equal only works for the first term. You cannot say this is approximately equal to that because it's an approximation. When it cancels, you have to redo the approximation. So if I put b equals minus 4, let me do it from the beginning and see. X square plus x plus 1 by x plus 1 minus x plus 4. You want this limit. You want this limit. Okay. So let us cross multiply and write this down. X square plus x plus 1 minus x square minus x, okay, plus 4x plus 4x plus x, sorry, plus 4 divided by x plus 1. This cancels out. And now if you notice, this is giving me 3x plus x. So it's giving me 4x plus 5 by x plus 1. But limit x tends to infinity. What do you get? Divide out the numerator and divide out the denominator. They are not exactly equal, but it doesn't matter because x goes to infinity. This will become 0, this will become 0. So 4 by 1, 4. Approximations works really well when it does not cancel out. When it cancels out, you have to go to the next level of approximation. Every time it cancels out, you have to do the next level of approximation. So Prajwal, I hope that is clear. Okay. So let us now move on to complex numbers. We have been doing a lot of complex numbers. So today I'm going to look at geometry of complex numbers using the polar form. Okay. So Adinaran asking ax plus bx is 20 locus of x is ellipse. See, if you take 2 points A and B and you look at a point x, you join ax and join bx. So this length plus this length is constant. Ax plus bx is equal to 20 basically means a to x, b to x length is constant. That is the definition of ellipse. Okay. So that is the definition of ellipse. Shashwat, complex numbers in Holland Knight is just the basics part. Okay. They don't do all this geometry and all that. So you need to do a lot more. So unfortunately, none of the books are going to be useful for that. Okay. So that's why I'm doing this. Let's move on. Let's move to, where was I here? Here, polar form. So, Argand plane, if you look at the Argand plane, you already know that complex numbers are points on the Argand plane, right? X plus Iy. This is R. R is equal to modulus of Z. The angle with the x-axis is theta. We call this argument of Z as theta. Now, if theta lies between, so you can go this way. If you go this way, it is negative angle. If you go this way, anti-clockwise, it's positive angle. So if theta lies between pi and minus pi, and pi is included. So that is, if you are talking about negative angles, negative numbers, negative real numbers, then this angle is pi. You could, of course, have called it minus pi, but here it's less than or equal to. So if you see here, I've written that theta must be minus pi to plus pi. Minus pi is an open interval. So that means you should not count minus pi. You start just after minus pi and you go around like that and you include till plus pi. Argument of 0 is not defined. That is, the angle is not defined because you can go any direction. No? So it doesn't matter. Now, whenever we talk about Z, if this is R and this is theta, we can also write this as R comma theta. We call this polar form. Sometimes people want to do this a little better. They say, okay, this thing is X, but R cos theta is X. This thing is Y. R sin theta is Y. So you can write Z as R cos theta plus I times R sin theta. Or we can write it as R times cos theta plus I sin theta. This comes up so many times that we like a new name for cos theta plus I sin theta. We call it cis theta. What is cis theta? Cos theta plus I sin theta. Cos theta plus I sin theta. So people take C, then they take I, and they take S, and they say cis theta. What is cis theta? Cos theta plus I sin theta. So Z can be written as R times cis theta. R times cos theta plus I sin theta. So this is also called polar form. So the word polar form is used in many different ways. So when we say polar form, this is polar form. This is also polar form. And there is one more polar form. Euler discovered that cis theta, which is cos theta plus I sin theta, no, that is not what he discovered. He discovered that you can actually call this e to the power of I theta. Okay. It is a definition if in one way, it is a discovery in another way. There is reason behind this definition. Okay. I'm not going to derive all that. I'm not going to show you that. Exponents behave like exponents. A to the power of m into a to the power of n is a to the power of m plus n. A to the power of m whole power n is a to the power of m into n. It must satisfy all of that if you're talking about exponents. Cis theta satisfies everything. So cis theta into cis phi is cis theta plus phi. You can show that by multiplying cos theta plus I sin theta into cos theta plus I sin phi, cos phi plus I sin phi. You can use the trigonometry formulas and show this. Cos phi plus I sin phi. No, that is the definition. No, this is cis, this is cis. You can show that this is true. It is called De Moivre's theorem. De Moivre showed this simple statement. But if you think in terms of exponents, it becomes easy. E power I theta into e power I phi must be e to the power of I theta plus I phi, which must be e to the power of I theta plus phi, which must be cis of theta plus phi. But what is cis of theta plus phi? Cos of theta plus phi plus I sin theta plus phi. So thinking like this makes a huge difference. E power I theta is cos theta plus I sin theta. It is not there in your syllabus. But trust me, knowing this makes complex numbers so much simpler. Okay. Because then you know all the laws of exponents. You don't have to remember De Moivre's theorem at all. You just have to simply say, okay, everything is e power I theta. So therefore, just simply add up whenever you're multiplying. Add up the angles when you're multiplying. Notice what is happening. So cis theta into cis phi. When you're multiplying two complex numbers, angle theta, angle phi, if they were cis, both were basically unit. If you take cis theta, it is cos theta plus I sin theta. No. What will be its modulus? Root of cos square theta plus sin square theta, which is of course 1. So it's a unit circle. So cis theta, the angle is basically angle theta, but for a unit circle. So when you multiply two of these, you will get theta plus phi. This angle will be theta plus phi. So all you are doing when you're multiplying by a cis theta or e power I theta, you are increasing the angle of the complex number by theta. So that's what you know with z. No, if z was here phi, if I multiply by I is e power I pi by 2, 90 degrees. So that means this fellow will turn by 90 degrees. If you multiply by I again, it will turn by 90 degrees. Every time you multiply by I, you are turning by 90 degrees. Every time you multiply by e power I theta, you have z here. Okay. If I now look at z e power I theta, it is going to be this fellow turned by angle theta. This point is z e power I theta. This angle is theta. This angle, I don't know what it was. Let's say phi. So if z was r e power I phi, you are multiplying r e power I phi by e power I theta. It will become r e power I theta plus phi. So writing z as r e power I theta is also called polar form. So what does that mean? That means this is r, the modulus is r, and the angle is theta. That's what this is. So if I do z1, z2, I'll get r1, r2, e power I theta 1 into e power I theta 2, but that will mean e power I theta 1 plus theta 2. That's it. The angle has basically become theta 1 plus theta 2. You just simply, whenever you're multiplying two complex numbers, you are adding up their arguments. So we also can write this. You can, not by any angle. Whenever you multiply any complex number, also you're rotating. But the point is, okay, whenever you're rotating by, when you're multiplying by e power I theta, you're only rotating. If you're multiplying by z2, you are rotating, but z2 may be 2 times e power I theta. So that after you rotate, you are doubling that length. It may be 0.5 times e power I theta. So after you rotate, you are making the length half. So R1, R2 is a product. It is just real number product, right? Theta 1 plus theta 2. The angles are multiplying. So we write this. You can write a lot of theorems. But once you write this e power I theta, problems get solved so easily. Because argument of z1, z2 is argument of z1 plus argument of z2. Okay, you can come up with all these types of things. What is this saying? E power I theta 1 into e power I theta 2 is e power I theta 1 plus theta 2. But what is this theta 1? What is that theta 2? So this is going to be theta 1 plus theta 2. This is going to be theta 1. That is going to be theta 2. Notice I'm using small a in argument. Small a just simply means one of the various angles. Need not be principal angle. Principal angle means you should only count between minus pi and plus pi. But if you just say small arc, you could have gone around 2-3 times and then arrived here. So I could have said 2 pi plus theta, 4 pi plus theta. These are all arguments. But only this angle theta between minus pi and plus pi, that is capital argument. That means principal value. And you can see it here itself. If this was z, okay, you go down like this. It's a reflection, no? This distance equal to this distance. So this is conjugate of z. A plus ib, a minus ib. If this angle is theta, this angle is minus theta. Okay, what is the conjugate of e power I theta? e power minus I theta. Okay, the conjugate of e power I theta is e power minus I theta because you're just simply turning the angle this way. This is minus z. What about its angle? Minus z's angle. It is not minus theta. This is the angle. This is the angle. This is theta. This is theta. So this angle, well, what is that angle? Theta. So this angle should be pi minus theta, but in the opposite direction. So minus z, argument of minus z is how much? Argument of z conjugate is minus theta. Argument of minus z is minus of pi minus theta or theta minus pi. Argument of minus z, theta minus pi. Similarly, you can do argument of minus z conjugate. I don't want to look at that. But basically, I hope you have understood the key idea here. Okay, so 2 points I want you to remember. 2 points I want you to remember. One, okay, you can first treat complex numbers as vectors. Okay, but you can do more. You can do more. This has r, this has angle theta. This complex number z can be written not only as r cis theta, cos theta plus I sin theta, it can also be written as r e power I theta. So this is the real polar form that I'm going to deal with, because in this form, a whole lot of things you don't have to even show. If you know this, then z1, z2 is r1 e power I theta 1, r2 e power I theta 2. So that is basically r1, r2 e power I theta 1 plus theta 2 from exponents. So therefore, modulus of z1, z2 is modulus of this, right? Modulus of this is just r1, r2. What is r1? Modulus of z1, modulus of z2 is r2. Because modulus, what is modulus of r e power I theta? R. Because modulus of e power I theta is 1. E power I theta lies on a unit circle. Suppose I had a unit circle. Let me draw this circle. E power I theta lies on that circle. This is not the unit circle. Okay, that is the radius r. So let me say that this was the unit circle. E power I theta will be this. This point will be e power I theta. If this radius is 1, e power I theta. Z is r times, r is this length, no? This length is 1, that whole thing is r. So r times e power I theta. Modulus of e power I theta is 1. So what is modulus of z1, z2? Modulus of e power I theta 1 plus theta 2 doesn't matter, no? Because it's still going to lie on this circle. So this is what you get. Argument of z1, z2. Argument is this thing. So theta 1 plus theta 2, which is argument of z1 plus argument of z2. 1 by z1, 1 by z1, 1 by r1 e power I theta 1, which is 1 by r1 e power minus I theta 1. No, because this fellow goes up, it becomes minus. So what is the argument of 1 by z? Well, it is minus of argument of z. Because theta is argument of z, minus of theta 1, so argument of z, minus of argument of z. Of course, modulus, you can always say modulus of 1 by z is 1 by r1, which is 1 by modulus of z. So all these things become obvious once you recognize that you can write z as r e power I theta, and you can do all the exponent stuff that you were doing earlier. Using this, omega, when you say x cube is 1, cube root, right? Omega, basically, if I cube it, I must get 1. If I cube 1, the angle is 0. E power I 0 cube is e power I 0. That's nothing big. But if I come back here, I can also say e power I 2 pi, right? Sorry. E power I 2 pi is also 1, no? Because if you come back, you'll get e power I 2 pi. So omega is e power I 2 pi by 3. Omega square is e power I 4 pi by 3. That's why the angle was 2 pi by 3. What is 2 pi by 3? 2 pi by 3 is 120 degrees. Remember last class I did this? So this is omega. And then 4 pi by 3, that is omega square. This is another 2 pi by 3 this way. So 2 pi by 3 plus 2 pi by 3 is 4 pi by 3. And you can see why if I square this, what's going to happen? You'll get this. So omega square is e power I 4 pi by 3. And what about omega cube? E power I 2 pi by 3 cube. So e power I 2 pi by 3 into 3 cancels out e power I 2 pi. What is e power I 2 pi? Cos 2 pi plus I sin 2 pi. Sin 2 pi is of course 0. Cos 2 pi is 1. So 1. So omega cube is 1. In fact, this should now start telling you what should be the 4th roots of unity. What should be the 10th roots of unity. All comes from e power I 2 pi. Suppose I want to say 7th roots. Suppose I say x to the power of 7 has to be 1. Then you write 1 as e to the power of I 2 pi. Take the 7th root. X is e to the power of I 2 pi by 7. And you can see that if I take this to power 7, it will become 1. But not only this, e power I double this, no, because you square it. 4 pi by 7 is also a root. E power I 3 times, cube this. So that means 6 pi by 7 is also a root. E power I into 4, 8 pi by 7 is also a root. E power I 10 pi by 7 is also a root. E power I 12 pi by 7 is also a root. E power I 14 pi by 7 is also a root. 14 pi by 7 is basically e power I 2 pi, which means 1 is also a root. How many roots did I get? 1, 2, 3, 4, 5, 6, and of course our usual 7. This has 7 roots. I found all of them. Okay. All of them are making angles like 2 pi by 7. What is 2 pi by 7? It will be some angle here. Then next one will be somewhere there, right? 4 pi by 7 will be somewhere there. Then somewhere there. Like that you will get. Okay. So 1, 2. This is of course 1. So 1, 2, 3, 4, 5, let's say. And then let's say this is 6. And then that is the 7. I don't know whether it's here or this side. What is that fifth one? 10 pi by 7. Is it 3 pi? 3 by 2, is it more than 1.5? No, right? 10.5. So it's this way, just close to this. Then the next one is here. Now each of these angles is 2 pi by 7. 2 pi by 7. Right? So this one, this one, this one, this one. So you can keep doing this for 9, 12, 13, 15, whatever. So how many 7th roots of unity will you have? 7. What are they? E to the power of I 2 pi by n. Nth root will be this. Then 2 times this, 3 times this, all the way till n times this. One of them you can say 0 times this also. Okay, so put k. K goes from 0 to n minus 1. Or from 1 to n. Both will give you the same answer. Anyway, we'll come to all that as we move on. Let us start doing some problems. That way we can understand better. So this question says, modulus of z is 6. Argument is pi by 6. Write this and write this. Okay. Easy. I'll give you a minute. Come on, quick. So this e power I pi comes up in physics, in Schrodinger's equation, in lots of places. E power I theta is cos theta plus I sin theta. Okay. Yes, this complex numbers, e power I theta, dramatically changes how you understand it. Okay, it suddenly makes it vectors and geometry. You have to think in those terms, makes things a lot easier. Yashwant, I think I remember this question. Not exactly sure the wordings and so on, but yeah, I think I know what you're talking about. If A and B are complex, it can be anything, no? So you have 2 variables. You can choose what you want to make it work. Only when you say it's real, that means A contributes 0 to the real value. No, the imaginary value. So B must contribute just right for the imaginary part on both sides. So that's why. If you make it complex, then you can't find the answer. It can be anything, two variables. Good question, Karthik. Very good question. Complex numbers were invented before vectors were invented. In fact, vectors, the main reason they came up with vectors was not for two-dimensional. For two-dimensional, complex numbers were always there. For three-dimensional, complex numbers does not work. No. So therefore, I think it was, I'm not sure it was Hamilton or who else. They were trying to extend the complex number system and they found it was very difficult. So they came up with something called a quaternion system. Why was it so difficult? Nowadays we have vectors. Why is it so difficult? Because they assumed that you must have vector division. Complex numbers allows for division. So they wanted vector division. Vectors, you notice vectors has dot product, you have cross product, you have multiplication, no division. No. So this vector division was causing trouble. So they came up with a system which allows vector division. But beyond two system, like two planar system, complex is enough. For three dimension, you needed actually 4 dimensions, which is the quaternion system. 3 dimension doesn't allow for it. But that's too complicated. So then finally people decided, let's not have division in vectors. Then vectors became possible. So that's why vector algebra came later. In fact, it is a derivation in some sense from quaternion system, but without division. So what is the difference between complex numbers and vectors? Well, vectors does not allow division. Complex numbers allows, but vectors easily extends to 3 dimension. Complex number does not. So that is the problem. So with complex numbers, see, number system, you want division. You can live with vectors not being division. But how can you say numbers don't divide? Multiplication is that, division is not that, doesn't sound right. So that's why people are like very hesitant to come up with vectors. But now that you have vectors, we may as well use vectors for 2 dimension, 3 dimension, everything else. But complex number would have been a nice replacement to 2-dimensional vectors, but unfortunately cannot become 3-dimensional. Okay, so therefore we don't use it today. So we use vectors when we talk about certain things, and then we use complex numbers for other things, but they're very closely connected. So in JEE, they won't give it to you as e power I theta, but they'll give you problems where if you know e power I theta, the problem solution will be easy. Just a plus ib will be too long. No, 2D vectors we can't divide. Vectors we cannot divide. Complex numbers we can. To do this complex number division, you must have that 1 by I becomes minus I. That rotation angle and all that you must have. So it is there in complex numbers. You see it. But vectors, pure vectors, are different from complex numbers. Anyway. So can we please go ahead? This question hopefully is easy. So I'll just go ahead and solve this. And I'll give you time for the others one. Ready? Modulus of z is given. Modulus of z is 6. Angle is given pi by 6. What is pi by 6? Pi by 6, 180 by 6, 30 degrees. So this is z. What is the x value? 6 cos 30. What is the y? 6 sin 30. 6 sin 30 degrees is 6 into half, 3. This is 6 into root 3 by 2, which is 3 root 3. So z is 3 root 3 plus 3i. Z conjugate is 3 root 3 minus 3i, of course. But I could have written z conjugate as 6 e power minus I pi by 6, which would have been 6 cos minus pi by 6, minus pi by 6 cos pi by 6, same thing, right? Plus I sine, right? 6 times I sine minus pi by 6. What is sine of minus pi by 6? Minus sine, right? Minus sine pi by 6. So you'll see 6 cos pi by 6 is root 3 by 2 plus I into 6 into minus half. And you will see that this basically is 3 root 3. minus 3i z conjugate. Of course, you don't have to do this work because once you write it in this form, directly you can write it. But I want you to understand that z conjugate is nothing but z conjugate is r, same r, e power minus I theta if z is r e power I theta. Only thing between z and z conjugate is that the angle becomes minus. Let's move on to the next question. Quickly do this question, 1 minute. I have prepared, I don't know, some horrendous number of questions. 26 questions. So there are 4 topics in mathematics that I really enjoy personally. Limits, complex numbers, calculus, differentiation, integration. Okay, I mean limits is also part of calculus, but differentiation, integration. So these are 3 important topics. Then I also like sequence series and things like that. But basically infinite series I really enjoy. But unfortunately, I don't get to teach that much. Calculus, because I take a large part of the calculus classes. So complex numbers, whenever I sit down to create questions, I end up creating too many. So 26 is too many questions. Okay. So, but let's go ahead. Please do this quickly. Let's quickly move on. Okay. From now onwards, I'll start moving fast. Quick. Polar form, if you want, you can do cis theta. No problem. Coordinate geometry, I like it, but not that much. It's okay. I use it. It's not as much fun. I like to do coordinate geometry using vectors and complex numbers. So, but many people think that is cheating. Shall we go? Easy, right? Yes. Jaswant, yeah, I know this, what he did. Ramanujam said that. But Ramanujam, very clever fellow, obviously. So what he said versus what he did, that is sometimes little hard. You write it as cis, no problem. E power I theta, cis theta, both are the same. Okay. So Ramanujam did not define what he meant by the summation. Usually we mean convergent series. Otherwise, you'll have to define second level, third level convergence. There are also series that you can talk about, like Ramanujam also talked about 1 plus 2 plus 3 plus 4 is minus 1 by 12. 1 plus 2 plus 3 plus 4, positive numbers, growing positive numbers. There he talked about what we call today analytic continuation. Vector algebra is a brilliant thing to learn, Zuhair. That's a very important topic. Anyway, enough. Let's continue with this. If you see this, I can quickly write this as 4 plus 4i. You can see that there is an isosceles triangle sitting here. 4, 4. So what is this angle? 45 degrees. 45 degrees means pi by 4. So immediately I will write z as this length. Well, this is 4, this is 4, this is 4 root 2. So 4 root 2 e to the power of I pi by 4. I pi by 4. Okay. Or you can write it as 4 root 2 cis pi by 4. Do it as e power because your brain will remember exponents. So therefore it will be very simple. What is the argument of z? Capital A. So principal value pi by 4 is between minus pi and plus pi. So that is correct. What is argument of z conjugate? Minus pi by 4. Because z conjugate is going to sit there. That is z conjugate. What is argument of minus z? Well, minus z is there. So this is going to be 45 degrees. But this is the angle I want, 135 degrees. So that is 3 times 45, but in the minus direction. So argument of minus z is minus 3 pi by 4. Minus 3 pi by 4. And then argument of minus z conjugate, which is going to be there. Well, this is 135 this way. Right? So argument of minus z conjugate, minus of z conjugate. So z conjugate, minus always means reverse. If you have this vector, minus will mean this. So if this was z, this will mean minus z. If this is z conjugate, this is minus z conjugate. But the angle always is from the positive x-axis. So you have to go this way. So 3 pi by 4. And you want to express all this in polar form. No big deal. Z conjugate is 4 root 2 e power minus I pi by 4. Okay, that is the Z conjugate. Z I already wrote. Okay, now if you want to write minus Z, it is 4 root 2 e power minus 3 pi by 4. Notice something. This R is always positive. The negative comes in the angle. Sorry, you have to put an I. So the minus comes from the angle, not from R. R is the length. By definition, R is magnitude. So never remember this is always positive. Notice here also it's positive. Minus Z, I could have written minus Z. If some of you thought minus Z was minus 4 root 2 e power I pi by 4, statement wise it's correct. Correct, but not polar form. Minus 1 is e power I pi. Okay, you can also write it as e power minus I pi. Both are correct. So if this minus 1 has to be taken inside the e because this has to be positive. So minus Z, if you want polar form, it is 4 root 2 e to the power of I pi plus I pi by 4. But then the angle will become greater than pi. You don't want that. So you can also write it like this. You can subtract 2 pi if you want, but I'll write it like this. E power minus I pi plus I pi by 4. And notice this is going to give me minus 3 pi by 4. So 4 root 2 e power I 3 pi by 4. So what is the angle? Minus 3 pi by 4. This is the correct polar form. Polar form is always r cis theta. Theta can have negative value, it can have positive value, it can be greater than pi by 2. You can do all that. But the r cannot be negative. Keep that in mind. Minus Z conjugate, angle is this. So 4 root 2 e power, the angle is just plus 3 pi by 4. 3 pi by 4 I or I 3 pi by 4. Notice the angle is positive. This is the positive angle. Here this is negative angle. This was how much? Minus Z. But all of the cases R is positive. So these are tricky points. Sometimes people forget that. Let me emphasize again, R is positive. Sometimes J will make a question around that. Can you quickly do this one? Z1 is given, Z2 is given. Don't forget R has to be positive. Okay. I want you to write all of these in polar form. Simple. Just spend a little bit of time. Do it. Come on, quick, quick, quick. Yes, Nigda, I'll give you a break, short break at 7:30. Don't ask me till then, okay? Anirudh, what are you answering? See, linear algebra is vector algebra. And vectors are not just 3-dimension. You can have 20-dimension vectors. Matrices and vectors are all part of the same system. So linear algebra turns out to be a very powerful tool. That's why we study vectors separately, because it's a subset of the linear algebra idea. Complex number is a different number system idea, which is kind of a superset of number system. They are connections, but they're different. Yes, please use this form when you're writing the answer. And we have logarithms with complex numbers, right? Roots, everything you can do with complex numbers. All of them will use this or e power I theta. Okay. So polar form is very critical for it. Shall we start? Okay, those of you who are looking at complex numbers from another book, that's a really good book. Okay, this is a little harder. Bernard and Child. There's Higher Algebra by Bernard and Child. That has some amount of complex numbers. It also has other things in algebra. A little hard. Okay, but very good stuff on complex numbers. Anyway, let's go on. So if you look at this one, Z1. Whenever you want to write all this, Z1 conjugate, etc., in polar form, best is to write Z itself in polar form. What is the modulus of Z? Root of 1 plus 3, so root of 4, which is 2. And what is the argument of Z? Argument of Z. Well, if this is the Y value, this is the X value, tan theta is root 3, right? Look at this. Root 3, 1, theta. Tan theta is root 3. If I look at this as a Z, right? So that means tan theta is root 3 means 60 degrees. So pi by 3. And so Z1 is 2 e power I pi by 3. Z1 conjugate 2 e power minus I pi by 3. What about minus Z1? You have to be very careful. If you write this is wrong. This is the starting point. You have to take that minus 1 as e power. So you write it as 2 e power I pi or minus I pi. In this case, because this is a positive angle, minus I pi will make it between minus pi and plus pi. Remember, your angle must be between minus pi and plus pi. Plus pi included, minus pi not included. So 2 times e power minus I 2 pi by 3. Angle you're talking about 2 pi by 3. You can see that very easily. No, this is Z. Minus Z has to have this angle. So this is the angle. R is positive. R has to be 2. So that is the value here. Similarly, you can do the same here. Okay. But if I take this thing, modulus is 1. I'm sorry, modulus is 2. Modulus Z2 is 2. But what is the angle? Angle 1 by 3. 1 by root 3. So tan of 30 degrees, which is pi by 6. And tan 30 is 1 by root 3. So that means Z2 is what? 2e power I pi by 6. Z2 conjugate will have a minus. Minus Z2 minus pi plus pi by 6. Minus pi plus pi by 6 will be 5 pi by 6. So I will write minus Z2 2e power I 5 pi by 6. That is e power minus I pi plus I pi by 6. Never leave the minus here. Join it. And so you'll get this minus pi by 5 pi by 6. Understood? I'm not doing this conjugate, just put a minus sign. So let's move on. Next question. Argument of Z is 0. What is argument of Z is 0? Think about the complex plane. These numbers are not argument of Z0. Only these numbers have argument Z0. These numbers have argument Z how much? If I use small arg, it will be minus pi or plus pi. But if I use capital arg, only plus pi. Okay, that's why 0 itself you can't define. Whether to say minus pi, plus pi, pi by 2, you can't say. So for 0, we don't talk about argument. If argument of Z is 0, this means Z is not equal to 0. First, cannot be 0, no, then you don't have argument. And secondly, Z has to be a positive, a real number. Not just real number, positive real number. Now you know the rest of it. Come on, quick. Quick, super quick. I've already told you the meaning. I told you the most important part. The rest of it you must do. Adinarayan, why did we define it to be minus pi to plus pi and not 0 to 2 pi? 0 to 2 pi would have been perfectly fine. The reason they wanted to do minus pi to plus pi is so that conjugate of Z, the angle can just be minus. So conjugate of Z comes so often. I'll show you that because it becomes so easy. Z is r e power I theta. Z conjugate is r e power minus I theta. Z conjugate is r square e power I theta minus I theta. So therefore this will cancel out r square, which is modulus Z square. Okay, it's so obvious when you see it this way, right? You know that Z conjugate is modulus Z square. That is because this angle and this one cancels out. So to say it cancels out, you can also say 2 pi minus I theta, but all that is messy, no? I theta minus I theta perfectly cancels, you know that. So just so that we can do this, they chose that we must have Z here, minus Z, Z conjugate here. So therefore, if this is theta, this is minus theta. That means you must define minus pi. If you go till pi, you must define till minus pi. So minus pi to plus pi. It could have been defined 0 to 2 pi, no problem. But defining it like this makes it a little more convenient for this conjugate. And we are going to use a lot of conjugate. That's right. Okay, I hope that's clear. Go on. Nikhil, complex numbers is it's very interesting to learn. It's good fun. And if you keep connecting it to coordinate geometry and vectors, you learn a lot. It's very useful geometrically. It is useful for algebra, it's useful for geometry. But limits is super important for the whole of calculus, the whole of functions. Understanding how functions behave, you cannot do without limits. So, in terms of utility value, limits is far more useful. In terms of interest value, complex numbers, I would say you need both. You don't want complex numbers, right? Yeah, this will be the last session on complex numbers, and we don't worry. There are some who don't like complex numbers. Anyway, yeah. Shall we go ahead, finish this? Let's see how many have finished this. So whatever I'm doing today, is not really required for your school. It is useful to know a little bit of it for JEE mains. But for JEE advanced, this is really, really useful. For JEE mains, yeah, you should know this. Whatever I did last class, you should definitely know. Whatever I'm doing part of this class, you should know. Okay. What's happened? Very few people have answered. I'll give a little more time. You guys want me to do trigonometry? I'll just find out. Usha ma'am?
Yes, sir.
We are asking whether we can do trigonometry next week.
So, okay, one more topic is there. We will do it, sir.
This is this trigonometry 4, no, all the series and all that stuff.
Yes, sir. Yes, sir. We'll do that next week, sir.
Anyway, let's come back to the questions, okay? I don't have to explain. I'm not going to explain what we have, why I like these topics. Just fun topics. I like all of mathematics. Most of mathematics. I won't say all. I don't like statistics. It's a very boring topic for me. I mean, I like to use statistics. But the statistics you guys have calculating mean mode, too many calculations. Oh yeah, you have to do derivatives. Wait a minute. I forgot. Usha ma'am, don't you have to do differentiation?
Yeah, we have differentiation also. Sir.
Let us do differentiation, then come to trigonometry. We should go forward, not backward.
Okay,
yeah.
Fine.
Let's do differentiation. I forgot we've not finished the portion. Okay. Yeah, so let us do differentiation. So suppose I tell you now Z is a real number. Okay, so that means I can just think of Z as R, right? So R plus, or I can just think of Z as X. So Z is only X plus 0i. So if I look at this, X plus 3i by 2x minus 5 plus I. 2x minus 5 plus I. The argument is minus I pi by 2. What does that mean? Minus I pi by 2. If this is plus pi by 2, this is minus pi by 2. So this number is not only imaginary, it is some negative k times I. Some k times I, right? Minus ki. This is what I have. Okay. So you just cross multiply. I mean, you can do simplification, but just cross multiply. So x plus 3i is equal to minus ki times this. So minus 2x minus 5 times k times I. And then this into this. I into I is minus 1. And then this minus and minus will become plus. So plus k. This is an imaginary quantity. This is imaginary quantity. This is real. This is real. So x is equal to k. First point, x is equal to k. Okay, so I should put x here. And so here 3 is equal to minus of 2x minus 5 into x. Because the real parts have to be equal, the imaginary parts have to be equal. If I had z, that was not possible. But because I have x is a real number, I can say real 3 times imaginary, right? I, real times I. So the imaginary must be equal. This is real, so that must be equal. K is real. K is not just real, it is positive real. So I'm putting R plus. Okay, so X must also be positive real. So we already know that it must be positive. So K is also positive, X is also positive. I use minus Ki, so that's okay. I use minus Ki. The number is minus Ki, but X is positive, K is positive. This is a quadratic, we can solve it. So if I take it to that side, 2x square minus 5x plus 3 is 0. And it's just a quadratic. So x is equal to minus b plus or minus root of b square minus 4 into 2 into 3 by 2a. How much is this? 6 4s are 24. So this is 1. So I'm going to get 5 plus or minus 1 by 4. 5 plus 1 is 6 by 4, 3 by 2. 5 minus 1 is 4. 4 by 4 is 1. So two possibilities are 3 by 2 or 1. Always check. Always check. Suppose I put 3 by 2, what happens to this? 3 by 2 plus 3i by 3 minus 5 is minus 2 plus I. Take 3 out. Actually, take 3 by 2 out, you will get this. Okay, this does not matter for argument. We need to look at this. Why not multiply by the conjugate? 1 plus 2i into minus 2 minus I. Okay, and if below I look at this, that is going to be 2 square 4 plus 1. Now this minus, let me pull it out, so I'll get 2 plus I, and if I cross multiply it, 2 minus 2, 2 minus 2, and then I into 1 is I, this is 4, so plus 4, 5i. There's a minus sign by 5. So this doesn't matter. So I get minus I. What is the argument of minus I? It is equal to, what is the argument of minus I? It is going to be minus pi by 2. So it perfectly works. So this is correct. What if I substitute x is equal to 1? I'll get 1 plus 3i by minus 3i plus I. And so if I now multiply this whole thing by I, multiply the numerator by I, denominator by I, this will become minus 1. This will become minus 3i. I can take the minus sign, make this 1 plus 3i. This will cancel out, giving you minus I. So again, the answer works. So this also works. So there are two possible values. X is equal to 3 by 2 and 1. Z is equal to 3 by 2 and 1. And both are positive, so both work. Okay. So two values. Remember, x has to be greater than 0. That was important. We got greater than 0. Both values were greater than 0. Let us go to the next question. Notice here. Capital ARG. Capital ARG is given. Okay, of z, 3 pi by 4. Then argument of z plus I by 5 plus 3i is pi by 2. Find z. I'm going to give you... How big is this question? I don't think it's very big. Okay. Try it out. Try it out. I'm going to give you 2 minutes. How did I... Second part is left. What is the second part? Find z. Okay. How did I write x plus 3i by 2x minus 5 plus I is minus ki? Well, that for the previous question, Sri Vishak, for the previous question, this quantity is this quantity. Right? I'm just substituting z is x. But argument is minus pi by 2. What is the meaning of argument is minus pi by 2? The number must lie on this. This is minus pi by 2. No. It must be in the bottom part of the y-axis. But all numbers on the bottom part of y-axis will be called minus yi or minus ki. Minus ki. K is positive. No. All numbers on the bottom y-axis is some real number times I, but the negative, no. Real number times I means what? Negative numbers. Because 3i will be up, minus 3i will be down. So I may as well call it as minus ki where k is positive. That's all. Okay. So I'm using that information that was given about the argument. So try this out. Varsha, capital ARG compulsorily has to be between minus pi and plus pi. Small ARG could be anything with that plus 2 pi. Whatever that actual argument, plus 2 pi, minus 2 pi, plus 4 pi, minus 4 pi, you can keep adding and subtracting 2n pi. Plus or minus 2n pi. You can do that. So what I'm going to, I'll just write this down. Okay, small ARG of Z is capital ARG of Z plus or minus 2n pi. Okay, you can add any amount of 2 pi angles or subtract any amount. Basically, if I told you that this angle theta is argument of z, capital argument of z, principal value. But same place I can arrive at going one trip and coming back. No. But if I did this, I would have got 2 pi plus theta. So 2 pi plus theta is also an angle that is called any of the various angles possible. So small ARG. There are many small ARGs. Capital ARG, there is only one. Why should I go only one trip? I now go one trip, second trip, third trip, fourth trip, then I come and stop here. So that means I did 4 times 2 pi plus theta. No problem. ARG of Z. How many ARGs of Z are there? Small ARGs? Infinite, because you can choose any n you want. So this is not a real good function. To make it a function, we use capital ARG. I hope that is clear. Okay, so we don't use small ARG. We use capital ARG to give you unique values. Well, if I gave you small ARG is 3 pi by 4, that is also correct. Because small ARG can be so many possibilities. But once I told you it is 3 pi by 4, that is the principal value. Okay, go on. Please find question 5, answer to question 5. So shall we start? Let us look at this. Just a second. Which question are we in? Fifth question, right? So the main point to keep in mind is that we have given you that something is argument is pi by 2. Whenever something is given with argument pi by 2, use it. How do I use it? Normal distribution, maybe sometime I can do that, but not now. Okay, so let us see. First move this thing down. The most important thing, 3 pi by 4 not greatly useful. Pi by 2 tells you that you must be somewhere here, which is y times I, and not just y times I, y greater than 0, positive number. What is y times I? This number has argument pi by 2, so that means z plus I. Notice what I'm doing. Everybody please think about it. If argument is pi by 2, that means the number must be e to the power of I pi by 2. Something into e to the power of I pi by 2, right? Or in this case, I will write it like this. I could have written the number must be r e power I pi by 2. Correct? Because if the argument is pi by 2, it must be this way. Now, what is e power I pi by 2? Cos pi by 2 plus I sin pi by 2. Cos pi by 2 is 0. I sin pi by 2 is 1. Right? So, sin pi by 2 is 1. So, this is I. So, e power I pi by 2 is I. But you already know that because you're moving like this, 90 degrees, this is I. So it is R times I, I'm writing it as Y times I. Okay? Now if I write it as Y times I, Z plus I is easy to find. Just multiply. 5Y I, 3I times YI is 3Y with a minus sign. So Z is minus 3Y plus 5Y minus 1 times I. This is Z. But its argument is 3 pi by 4. What does that mean? Z's argument is 3 pi by 4. Z must look like that. 3 pi by 4. So 135 degrees. This must be the Y value. This must be the X value. So X is negative. Y is positive. And X and Y are equal in magnitude, right? So Y is minus of X. Or X is minus of Y. Good enough? Or you can say, well, tan of 3 pi by 4 is minus 1. But tan is the Y value. Well, let me not call this Y value. Y dash X dash. Because I'm using Y here. So Y dash X dash. This is Y dash by X dash. Basically, the Y and Z of Y and X of that Z, Y dash and X dash, you can see that this must be 45 degrees and negative number. So that means this must be minus. So what does that tell you? That it tells you the X dash plus Y dash is 0. Because Y dash and X dash are opposites. So if I just took this is X dash, this is Y dash. If I add it, it must be 0. So minus 3Y plus 5Y minus 1 must be 0. So 2Y must be 1. Y must be half. Half. This is 1 by 2. But if Y is half, I know what is Z. Just substitute for Y. So Z is minus 3 by 2 plus 5Y. 5 by 2 minus 1 is plus 3 by 2I. Notice that this is minus 3 by 2 plus 3 by 2I. So this is where the point is. This is 3 by 2 and this is 3 by 2, but this is in the negative direction. So minus 3 by 2 plus 3 by 2I. And you can see that this angle is 45, this angle is 135. So which is 3 pi by 4. Understood? I started out by using this. You could have started out by using this. You can say, well, let's say Z was X plus IY. Argument is 3 pi by 4. So therefore, X must be negative and Y must be positive. They must both be equal. So I will write this as minus K plus I times K. I won't write X and Y. I'll use this. Then you substitute that here and see that this must have an angle of pi by 2. You could have started here and ended up there. But because it was pi by 2, I started there and ended up here. I didn't have to worry about two variables right in the beginning. I start only with one variable. Here also I don't have two variables. I have only one variable. Both are equivalent and both will give you the answer. So there's only one value for Z, minus 3 by 2 plus 3 by 2I. Let's see how many got that right. Question 5, no? Sanjit Dev has got this right. Siddharth Vijay got this right. Very good. Rishabh has also got this right. Adi Narayan got this right. Yashwant, I think what you wrote is not right. No, that's not right. No, Utkarsh, that's not right. Sai, that's right. Gayatri Achar, 3 by 5 is not right, Gayatri. Who else has got this right? Murari has got this right. Sri Vishak, no, not just cis. You have to have an R e power I theta. No, you're forgetting the R. You have to find the modulus of Z. Otherwise, you can't find Z. Okay. Actually, not too many. Gokul has got this right. Well, a few have got this right. Sanjana has got this right. Okay. Srinja Malik has also got this right. And Prajwal. Okay. Let's go on. Shashwat, you got this right? No, I didn't see your answer here. Shashwat's answer. You wrote it as root 3 by root 2. Correct. 3 by root 2. That is also correct. Okay. Vishnu Anand then has also got it right. Okay, he's written it in polar form. Okay, correct. Avani has also got this right. Good. Shashwat, Avani, all of you got this right. So some of you have written it in polar form. Did we ask for polar form? No. Okay. Yeah, if you want, you can write it in polar form. No problem. Let us move on. Let's move on. Most of this I've already told you, but I will just go ahead and do one small thing. Like vectors, you can add. Okay, you can add complex numbers. So if I have Z1 and Z2, just move this Z2 here. So if I say this is Z1 and this is Z2, to add, take this Z2 and move it here. Remember, Z2 is like position vector. It has to start at the origin. But when I move it, it is a parallel vector. This is not Z2. This is parallel to Z2. This was Z2. This point was Z2. This point is not Z2. This is Z1 because this is the origin. So Z1 plus Z2, this gives you Z1 plus Z2, parallel to Z2 and equal to it in magnitude. Okay, so this is Z1 plus Z2. Basically, just simply move it and you can get Z1 plus Z2. Very useful, very useful. And if I have two vectors, Z1 and Z2, this length or this arrow is Z1 minus Z2. Final minus initial. This is starting here and ending there. Final minus initial. Like you do vectors. Extremely useful. But is this the point Z1 minus Z2? No. If you want to find that, move it back to the origin. Move this arrow back to the origin like I've done here. So this point is Z1 minus Z2. This vector is Z1 minus Z2. So now we are talking about two things. Point Z and arrow Z. We are going to confuse you using both of these. So Z as a point has an arrow from the origin to that point. Z as an arrow can start anywhere and end anywhere, right? So if I took this arrow from here and moved it there, this arrow Z is the same as this arrow Z. But this point, if this was origin, this point is also Z. This point is not Z. No, this is not origin. So this point is not Z. If this point was A, this point is A plus Z. Whereas this point is just Z. This turns out to be very useful. That difference between two vectors is basically take these 2 points and find the distance between them, find the length between them. How is that useful? Because many questions will ask you this. What is this? It is the length of, you can say it is this point. You can say this point is Z1 minus Z2. So I want this length. But instead of that, you can say it is the length of this line, right? Length of arrow from Z2 to Z1. Okay, so modulus of Z1 Z minus Z2 is the distance between Z1 and Z2. Super useful. Why is it super useful? Because when you take circles, you want distance between the center and that point to be constant. So if I now think about a circle, okay, and let's look at an axis. And let me say that this arrow is the arrow that I'm interested in. This is the center. Now let us say that this is the arrow for some point on the circumference. Then this arrow, what about that arrow? Let's think. This is Z. This is, let us say, the center, which I will call as ZO. Okay, this is Z0. This point is Z0. This point is Z. What about this arrow? Z minus Z0. Is this the complex number Z minus Z0? No, this is the arrow Z minus Z0. If I move this arrow here, I may end up with a complex number, which I will get here. This is complex number, this point. Is Z minus Z0 point, complex number. Whereas this is complex arrow. Complex arrow doesn't have a starting point. No? Anywhere it can start. So it will end at different places. But it still has a length. What about the length of this complex arrow? Well, that is equal to the radius. So as this Z moves around, Z minus Z0 is R. Will always be true. If I was here or here or here or here, as Z moves around, Z minus Z0's magnitude is R. So Z minus Z0 is R is equation of a circle with radius R. Because what is Z minus Z0 magnitude? It is the length of the arrow from Z0 to Z. Z0 is a fixed number. Is the equation of a circle with radius R and center Z0. Notice how we can derive some simple theorems like this. The moment you see, you will be able to figure this out. Because if you understand Z minus Z0 is the arrow from Z0 to Z. Z minus Z0 is arrow, not complex number. Don't think of it as complex number. Arrow from Z0 to Z. Z0 is a point. Z is a point. Z minus Z0 is an arrow from Z0 to Z. It is also a point. It's a different point, far away point. But instead of thinking of it as a point on the complex number, if you think of it as an arrow from Z0 to Z, then the length of that arrow is always constant, is the statement. But when does the length of an arrow keep constant when you're moving things around? For a circle. So therefore, Z moves around in a circle, keeping the distance of Z from Z0 constant. Well, you know that's a circle with Z0 as the center. So this idea, Z1 minus Z2 is the distance. Very powerful. What is the argument? It is the angle made by that arrow with the x-axis. Okay, so the argument is the angle made by Z1 minus Z0, Z1 minus Z2 with the x-axis. So this angle is the argument of Z minus Z0. Capital R, small r doesn't matter. That is the argument with the positive x-axis. Well, x-axis is here, so you must bring the x-axis here and then take the angle. Understood? So from this you can derive a lot of things, right? We call this the triangle inequality. You know that for any triangle, this length plus this length is bigger than that length. Correct? But if this is Z1, this is Z2, this is Z1 plus Z2. So Z1 plus Z2 magnitude, which is the length. This is Z1 plus Z2, but complex addition, complex number addition, not magnitude addition. If I just did magnitude, that will be Z1 magnitude plus Z2 magnitude. Is this magnitude plus this magnitude equal to this magnitude? No. This magnitude plus this magnitude is greater. This is lesser than Z1 plus Z2, can be equal because you may also have both of them parallel. In fact, that will be the only condition where Z1 plus Z2 magnitude wise is equal. So this is called triangle inequality. Inequality. What about Z1 minus Z2? Oh, you can do that also, no? This is, let us say, Z1, this is Z2. What about that? Z2 minus Z1. Clearly, this one's magnitude is less than magnitude of this plus this. Z1 plus Z2. By the way, you can also do some subtraction. You can also do some subtraction based inequalities. Okay. But you can say Z1 minus Z2. Not approximation. This is take the greater value. Big minus small. Big difference we call it. Difference big minus small. These are all real numbers, remember. Z's are complex. The modulus is real. The difference between two complex numbers is always less than or equal to modulus of the difference is always less than or equal to modulus of the difference or sum, which is less than or equal to the sum of the two modulus. This is the difference. So, for example, if I say 3, 4, 5, 3, 4, 5, I'm just using right angle triangle. What we are saying is 3 plus 4 is bigger than 5, right? This is 3, 4, Z1, Z2. This is Z1 plus Z2, right? This is modulus of Z1 plus modulus of Z2. This is modulus of Z1 plus Z2. And this is greater than 4 minus 3. Why 4 minus 3? You can also do 3 minus 4, but take the bigger minus smaller. Of course, it's greater than 3 minus 4 anyway, right? Because that is becoming a negative number. So you take difference. I told you I'll give you a break. So now it's already 7:42. I want you to quickly look at this question. Look at this question. Try this out. I'll give you, now it is 7:42. Okay, so I'll give you 2 minutes for this question. So that'll become 7:45. And I'll give you, that's 7:43. I'll give you 5 minutes plus 1. Okay, so overall we will start the class at 7:50. So do this question number 6. Please do question number 6. Okay, geometrically, you can try that out. ABC. Very simple. Actually, do question 6 and question 7. I'm giving you 3 minutes. Well, not really. It's become 7:43. Okay, 2 minutes. I'll just do this, take a break. We'll come back to that later. Okay, we will start at 7:50. So shall we start? It's 7:52, 7:53. So let's get started. This is a very easy question. ABC represent these 3 points, right? This is A, this is B, this is C. So what is AB? AB, I'll put an arrow on top, starting at A, ending at B. So B minus A. So minus 3 plus 9i minus 2 minus 3i. You can also, of course, say these are all coordinates and I'm going to use coordinate geometry, but we are doing complex numbers. Why don't we just do that? So minus 3 minus 2 minus 5. 9i plus 3i is 12i. So modulus of AB is root of 5 square plus 12 square, which is 13. Similarly, you can do modulus of BC. What is BC? C minus B. So 5 plus I minus 3 plus 9i, which is 8, and that is minus 8i. So BC modulus is 8 root 2. Then what is AC? AC is A to C, right? A to C. So this minus that. So I'll directly write the answer. 5 minus 2 is 3. Okay, I minus of this is plus 4. 4i. So modulus of AC is 5. Root of 3 square plus 4 square, 5. So AB, BC and AC are these, right? Does that add up? Well, it's not a right angle triangle, need not be, no? So it's not a right angle triangle. So these are the 3 values, which is totally fine, because if you add them up, 13 plus 5 is bigger than 8 root 2. That's all you need. So they will anyway add up because there are 3 points that are given. If I have any 3 points that are given, definitely it will form a triangle. So you don't have to worry. So it will follow the triangle law. This was just to see how we can do this calculation. Let us look at this one. This is easy again. 7th question. Modulus of Z1 is 3. Modulus of Z2 is 4. And modulus of Z1 minus Z2 is 5. So what does that mean? Z1 lies on this circle, 3. Z2 is 4. And the arrow from, right, this is final minus initial. So from Z2 to Z1 is 5. So suppose I say that this was Z1, that is Z2, like that, let's say that is Z2, and this arrow is 5. This has length 5, this has length 3, this has length 4. So you know that this must be an right angle triangle, right? So this angle must be 90 degrees. So what I have drawn here is not right. So this is 3, this is 4, and this arrow must be 5. Because it has to be 90 degrees. I just drew this to say that 3 square plus 4 square is 5 square. So therefore, this must be 90 degrees. So what is the area of this triangle O? Well, this is Z1, this is Z2. What is the area of this triangle O, Z1, Z2? Well, half base into altitude. So area is half into 3 into 4. Half base into altitude. So 6. Okay. So that is the area. So I hope that is clear. Because Z1 minus Z2 is 5, just simply means that it is a line joining Z1 to Z2. Z2 minus Z1. Z1 minus Z2 means in the opposite direction. So that doesn't matter. We're only looking at the magnitude. This is Z1 minus Z2. Z2 minus Z1 will be in this. So basically, if this is Z1 and that is Z2, this arrow is Z2 minus Z1. This arrow is Z1 minus Z2. Final minus initial. That's all. But either way, the answer is still going to be 6. Okay? Let's move on to the next question. Can you do this one? Come on. 8th question. I'm going to give you a minute. Quick. Distance formula. Achyutan, I know you can use the distance formula and it's quite simple. But the idea here is Otherwise, I don't have to give you that question at all. No, I can directly go to a harder question. So basically, graded, I have just made sure that you do one or two simple ones. So you get the concept clearly. That's all. Okay. So the purpose is not for you to solve that particular problem. As we move on, if you have not got the concept that Z1 minus Z2 means the line between them, all that, right? Then later problems will become hard. Look at the 26th question here. Quite tricky. Okay. Yashwant, it is both. It is both. Yes, Anirudh, if it was not a right angle, you could have used Heron's formula. Okay, Yashwant, complex number is both. If you think of a point, then that means it's an arrow starting at the origin and ending there, and it's a point. But if you just decide to move the arrow, the point where it ends is not the complex number. The arrow itself is the complex number. You can use both. Okay, so two interpretations to complex number. Now everybody do question number 8, guys. Quick, quick, quick. The modulus question should not make the numbers plus or minus 1. No, not plus or minus 1. What do you mean by that? Modulus. It's a complex number. Its modulus is what you're asking. Yes, Shyam. Complex numbers can be modeled as vectors. Okay, and vectors can be modeled as complex numbers. Usually, nobody models vectors as complex numbers, but complex numbers as vectors, very powerful, very useful. Except you can do division in complex numbers that you can't do in vectors, and you can write complex numbers as e power I theta, right? R e power I theta. So therefore, usually those are additional things that are available to complex numbers, not to vectors. So don't use complex numbers in vectors. Well, you can think in those terms, but not very useful. So I'll show you this question. Actually, you can do this in a nice way. You can sit there and do this in a hard way, but you can also do it like this. So suppose I think of this arrow. Let's say that arrow was Z1 plus Z2. Okay. And let's think about another arrow, which is Z1 minus Z2. So suppose I look at an arrow like that, Z1 minus Z2, right? I will just draw some arrow here, let's say. This is Z1 minus Z2. Now, what about this arrow? What about that arrow? Or what about the reverse arrow? Let me do the reverse. Okay, let me go like this. What about this arrow? What is this arrow? This arrow is final arrow minus initial arrow, no? How much is this? Well, Z1, Z1 will cancel. This is 2Z2. So actually, Z1 minus Z2 plus 2Z2 will give me Z1 plus Z2. What is the length of this arrow? It is given as 8. What is the length of this arrow? It is given as 6. And what is 2 times Z2? 2 times Z2, the length is 10. But you know 6 square plus 8 square is 10 square. So that means this must be a right angle triangle. The angle between these two must be 90 degrees. So Z1 plus Z2 must look like this. And Z1 minus Z2 must look like this. And they must be 90 degrees. So if they are 90 degrees, Then if I look at Z1 minus Z2 plus Z1 plus Z2, I'm now adding, I'm not subtracting. That will give me, this is 90 degrees. No, that will give me, what is this? So Z1 minus Z2. This is Z1 minus Z2 plus Z1 plus Z2. And you can see the Z2 cancel. This is 2Z1. So 2Z1 is the hypotenuse. But Z1 minus Z2 length, you know, is 6. Z1 plus Z2 length is 8. So this 2Z1 should be root of 6 square plus 8 square because it's a hypotenuse, no? So this should be 6 square plus 8 square, which is 10 square. Root must be 10. That means modulus of Z1 must be 10 by 2, 5. Modulus of Z1 and modulus of Z2 must be equal. Let's draw the diagram again. So Z1 minus Z2 looks like this. At some angle, doesn't have to be like this. Let me draw it. Okay. Z1 minus Z2 must look like this. Z1 plus Z2 must look like this. Okay. And so this is, let me write, this is Z1 plus Z2, Z1 minus Z2. If you now duplicate this and move it here, that is also Z1 plus Z2. So now what is going to happen? If I now look at this arrow and look at this arrow is what? This arrow is 2 times Z2. Why? Because it is this minus this. Z1 cancels, it becomes 2 times Z2. This is Z1 plus Z2, right? Now this arrow, that arrow, they are falling one after the other. So Z1 minus Z2 plus Z1 plus Z2. So this is 2 times Z1. So this is 2 times Z1, this is 2 times Z2, but this is 90 degrees. So this is actually a rectangle. And you know the diagonals of a rectangle have equal length. So 2 times Z1 is 2 times Z2 in magnitude. So Z1 must be the same as Z2 in magnitude. They're not the same complex number, but both have the same magnitude. We have already been told Z2's magnitude is 5, so Z1's magnitude must be 5. Okay? So this is one way of doing it. Any other way of doing it? Lots of ways of doing it. I'm just telling you a couple of distance-based ways of solving this problem. Okay? So can I solve it some other way? Yeah, you can. You can do x plus iy if you want, but all that is extra work. This is much simpler. Okay. So basically, if you've got Z1, Z2 vectors, think of it as vectors. So Z1, Z2, Z1 plus Z2. I could have also done this like this. I could have said, hey, let this be Z1. I don't know what it is. Let this be Z2. I know that this Z2 is length 5. So if I put length 5 here, I don't know whether they're perpendicular, right? I don't know if they're perpendicular. So let's say this was Z2, 5. If I put this here, this is Z1 plus Z2. But if I put it like this, this is Z1 minus Z2. You can do that also. So this is the median of this triangle. Think about it like that. Now this is length 5. This is length 5. Okay. This length we have been told that is 8. This length we have been told that is 6. So this length is 10. 6, 8, 10 must be a right angle triangle. So this and this must be perpendicular. So these two must be perpendicular. Okay. So if I now draw, this is Z1 plus Z2. This is Z1 minus Z2. And then draw this. Take the midpoint. This is Z1. This is Z2. This is minus Z2. Now you know that this is a right angle triangle. So this is angle in a semicircle. This is the center. So this is equal to this is equal to this. Modulus of Z1 is equal to modulus of Z2. No? If I have a right circle, you know that angle in a semicircle is 90. You also know whenever this angle is 90, you can think of a semicircle with this as the center. So this side is equal to this side is equal to this side because they're all the radius. Okay. So we can use some of these geometry ideas and bring them into complex numbers. Understood? Let's move on to the next one. Come on, this I have already explained. What is the locus of all points satisfying this? It is a circle with center Z0 and radius R. Right? Because this is Z0, this is Z. Z minus Z0 is this arrow. Its modulus is R. So its modulus is R basically means it can move all over here. So Z0 is this point. Could be any point. Okay, Z minus Z0. Z0 is the center. All points Z. Locus just simply means move Z along, move Z such that condition is satisfied. How do you move Z along such that this condition is satisfied? Well, you have to move it along a circle. So this I have already explained. I'm not going to do this 9th question. 10th question. 10th question. Think about it and do. What do you think this means? 10th question. Shyam. Are modulus of Z1 plus Z2 and modulus of Z1 minus Z2 always perpendicular? Not necessary. Not necessary. Okay. So, for example, I'll show you why it's not necessary. I'm going to have a very large Z1 and a very small Z2. Then what happens? Then you will see that it is not perpendicular. I'll show it to you directly. So that is Z2, right? I'm drawing it, constructing it and showing directly. So that is going to be Z2. Let us paste it again. But this time, I'm going to flip it around. What is that? Minus Z2. So I've got Z, let me write it here, Z1, Z2, this is Z2, this is minus Z2. So therefore, what will this be? Z1 plus minus Z2. So obviously this one must be Z1 minus Z2. And what about that fellow? Let's put it there. It's not correct, so I have to move this fellow down. So not like that. Like that. Okay, so now what is this? Z1 plus Z2. Z1 plus Z2. And what about this? Z1 minus Z2. I have actually constructed. Is this angle 90? No. Okay. So last time, why was it? Because Z1 and Z2 are equal. Z1 plus Z2 is perpendicular to Z1 minus Z2 if Z1 modulus is equal to Z2 modulus. Why? Why? Because this length and this length will be equal, but this length is equal to this length. Let's see that. Suppose I had Z1 and let's say I have Z2. They now don't have to be perpendicular. They just have to be equal in magnitude. That's all. Suppose this was, okay. So suppose these two are equal and then I want to flip this. So they're equal. I'm going to just put that there. So now notice what is going to happen. If they were equal, I'm assuming I've constructed equal. So this is Z1, this is Z2, this and this will have to be perpendicular. Why is that perpendicular? Because notice, I told you that this length is equal to this length. This is Z1, this is Z2. This is minus Z2. Minus Z2 is equal to minus Z2, right? So all three are equal. So if I keep this and I draw a circle, the circle will pass through this point. But angle in a semicircle is 90 degrees. So this has to be. This is true if this happens. And if this happens, that is true. Both are if and only if. Got it? So Z1 plus Z, this is a geometry theorem. If modulus of Z1 is equal to modulus of Z2, that means the length of Z1 and length of Z2 are equal. That means Z1, Z2, Z minus Z2, right? You can draw this. You can see that I'm creating a circle. And the angle in a semicircle is 90 degrees. This is Z1 plus Z2. this is Z1 minus Z2. So this angle between Z1 plus Z2 and Z1 minus Z2 must be 90 degrees. Okay. So whereas in general it's not true if the magnitudes are different. If the magnitudes are different, this fellows will not be perpendicular to that. That was not the question, but anyway, since you asked. So let us go ahead, look at question number 10. How many have answered? Adinarayan, the whole of electricity, particularly AC circuits, you model it as complex currents and complex voltages. So whole of signal processing and this is all done with complex numbers. So I can't tell you where it is used. It's used everywhere. Engineering is entirely complex numbers. Shyam, the longer method I don't want to do. Yeah, you can just do it as x plus iy, substitute and do it. It's a long method. You will get it, but it's little long. See, 8 and 6 form a right angle triangle. But if that thing wasn't 10, no, Z1 plus Z2, Z2 was not 10, Bhaskaran, then it wouldn't have been a right angle triangle. So you have to be careful with that. Complex numbers are used in Fourier transformation. Yes. Okay, let's go look at question number 10. You guys are not doing complex numbers. You're asking me other things. Okay, let's see. Z minus Z1 must be Z minus Z2. Let me just think about this. Let's pick up Z1 and Z2 and put 2 points. So let's say that this fellow was Z1. And let's say this point somewhere here was Z2. Let me join these two. Okay, since it's not joining properly, I'll just move it here. Okay, so now I've joined this line between Z1 and Z2. What exactly is the question saying? The distance of a point Z. Let's think about some point. Let's say I take this point Z. The distance of Z from Z1 must be equal to the distance of Z from Z2. Is that true for that point? No. Midpoint? Yes. Only midpoint? No. All the points that are on the perpendicular bisector. Okay, let me just turn this around a little bit. All the points on the perpendicular bisector. If Z lies there, then you know that it will be true. It is not true for that point, no. But it's true for this point. If I pick a point here, or there, it is true. Why is it true? Because this distance is equal to this distance. This distance is equal to this distance. This distance is equal to this distance. Right? If you go anywhere else like there, this distance is more, this distance is less. If you go here, somewhere on this side, this distance is less, this distance is more. If you are on this side, the distance to Z2 is less. If you are on this side, the distance to Z1 is less. You must be right on the perpendicular bisector for the distances to be equal. So therefore, what is the locus? That means all the points for Z. How can Z move? Z has to move on the perpendicular. Locus is the path on which Z has to move, perpendicular bisector of Z1, Z2 line. Z1 to Z2 line. You take this perpendicular bisector, these two are equal, this is perpendicular. Okay, so this point is of course one of the points which is equal distant from, so meaning, look at the meaning. Distance of Z from Z1, it's like saying there is a point B which is equally distant from A and C. So suppose I have A and C, I want points that are equidistant. Well, they have to be all on the perpendicular bisector. That's all this is. Interpreting this is important. Distance of Z from Z1 is equal to distance of Z from Z2. So Z must be in the perpendicular bisector of the line joining Z1 and Z2. So Z1, Z2 line, take the perpendicular bisector. That's where Z lies. Let's go to the next question. 11th question. I've told you A is Z1. A is Z1. This is not A of Z1. Point A is represented by Z1. Point B is Z2. Point C is Z3. Complex representations are these. So ABC forms a triangle. You don't want to say Z1, Z2, Z3 forms a triangle because that looks like multiplication. You could have said that, but okay. Find the type of triangle if this happens, this happens, this happens. Think about it. Omega is e power I 2 pi by 3. So multiplying omega by Z, rotate by 2 pi by 3, which is 120 degrees in this direction. Right? If you have a Z, when you multiply by omega, turn by 120 degrees. This point is omega Z. IZ means turn by 90 degrees. Omega Z turn by 120 degrees. That's all. Omega is very powerful because you can turn by 120 degrees. So go ahead, please do this. Quick. Okay, I'm going to give you two. How much time should I give you? Maybe 2 to 3 minutes? 3 minutes. 3 questions, 3 minutes. Come on, quick. Jaswant, it is not used in Riemann hypothesis. Riemann hypothesis requires complex numbers. Okay, it's stated in terms of complex numbers. So, complex numbers very useful in lots of places. Today's mathematics cannot be done without complex numbers. So, there's no question of whether it's useful. So, okay, those of you are finding today's class hard, it is an advanced level. I still have 3 more levels, 5, 6, and 7, which I won't do now. We'll only do it when we get to JE advanced. Okay. But basically, this itself is an advanced level. So this is somewhere between JE mains and JE advanced and reasonably tricky questions. So don't worry if you're finding it hard. The argand vectors, just get introduced the first time you're seeing it. So don't worry. Okay. So you'll get there, Srividya. So just don't worry about it. Keep trying 2, 3 times, then it will go ahead. Shashwat, you will learn complex numbers. Whatever I have done, you will learn it in the first year in IIT. Okay, you have a complex analysis thing, I think first year or second year. I think it's the first year itself. Second semester, I think there is complex numbers, at least IIT Madras. So you learn it throughout. Electrical engineering without complex numbers, you can't even start. And their root of -1, they call it J because I is used for current. So therefore, current is important for electrical engineering, right? So therefore, everywhere they'll use J as the complex root of -1, but used heavily. No Shyam, no complex numbers in class 12. But use of complex numbers in physics is there in class 12. Anyway. De Moivre's theorem is there in your syllabus. They've removed it from your syllabus, I think, for 11th standard because of this pandemic and all that. De Moivre's theorem is very much there for JE mains because it's there in your syllabus. Okay, I think it's Moivre's. There's a V somewhere hanging around, but anyway, let's not worry about spellings. Prajwal, what is your doubt? Huh? No, Prajwal, no, you can't do that. See, Z1 and Z2 are fixed numbers. The locus is for Z. Z is moving. Z1 and Z2 are fixed. So distance of Z from Z1 must be equal to distance of Z from Z2. The distances can change. 3, 4, 5. It's not circle. It's not a circle. Okay. Enough. Now, guys, finish this question. I'm going to give you another minute and then I'll start.
Liking
Usha, ma'am.
Yes, sir. Yes,
I don't
sir.
think I'm going to be able to finish this sheet.
Yes, sir.
Can I just take a vote? Take a vote.
Ah,
If they want me to continue with this sheet next week, okay, there are some reasonably important questions, or I can move to differentiation. Just take a vote based on whatever they're saying. We will
or
decide.
shall we do for 1 hour this and continue the derivative? Is that fine, sir?
1 hour
Is that
we cannot
possible?
finish. 1 hour we can't finish. This is the rest of it will take at least one class. No, you can ask them.
Oh, okay.
We can do
We'll
differentiation
take a
and come
vote,
back
sir.
to it later also.
We'll send it.
Sorry, there was, I think, a cut.
Yes, sir, there was a
Yeah. No. So, Usha ma'am, we can do differentiation. If most people want that, we can do differentiation. We can come back to complex numbers. It's a good idea to, yeah, we can do that. Let's do differentiation and come
complete
back.
all the topics first. Then, when the time permits, that will be
No
fine,
problem.
sir. Yeah. Yes.
No problem.
Yes.
Yes, the old NCRT has De Moivre's and cube roots. When I was studying, I had that, but they removed all that. Anyway, John Marshall, I don't want to give all the other worksheets. People will start pestering me, asking me for solutions. So I'm not doing that. When I discuss
Sir,
that, I'll come back.
Because
I
you
also
said
have lots of
7,
limits. I have lots of limits, lots of integration worksheets I'm never able to finish. So we'll do that. Don't worry. Let us do this problem. And then we can come back and look at the rest of this sheet. I'll come back and do later. No big problem. So what is the meaning of this? Okay. The distance from Z1 to Z2 is equal to Z2 to Z3 is equal to Z3 to Z1. Come on. This must be equilateral triangle. I don't even have to draw it. Hardly anything. Z1, Z2, Z3. So I've got this. I know that Z1, Z2 square. So let's call that as, basically we are saying Z1, Z2, Z2, Z3. So that means this must be Z2. This is Z1, Z1, Z2 square plus Z2, Z3. This distance square is equal to Z1, Z3 square. So obviously this must be a right angle triangle. With right angle where? With Z2 90 degrees. Z2 is 90 doesn't mean Z2 is 90 degrees. This is Z2. There's no 90 degrees for Z2. This angle is not 90. Z1, Z2, Z2, Z3. This angle is 90 degrees. I mean, when you say ABC angle C, you say angle B is 90. So basically Z2 is B. What about this? Z1 plus omega times Z2 plus omega square times Z3 is 0. What does that mean? That's a little weird. No? So, if I think about Z2, omega times Z2 is just this. This is Z2, that is omega times Z2. Wait, let me make the angle more. Omega times Z2. Omega square Z3 omega square Z3. I don't know where Z3 is. Okay. But omega square Z3 will basically make an angle of, from Z3, I have to turn 120 degrees. This is omega square Z3. And we are saying Z1 plus omega times Z2 plus omega square Z3 is 0, which means this plus let us say something like that, that is Z1, adds up to 0. All three of them add up to 0. What does that mean? That means Z1 arrow plus omega Z2 arrow plus omega square Z3 arrow adds up to 0. Right? The three things add up to 0. And what is the angle between Z2 and omega Z2? This angle, this is 120 degrees. Okay? So if I took this and turned it around, then I will get 120 degrees. So I've got now Z1, omega Z2, omega square Z3. So these three add up to 0. That's what is given. Okay? Then what? How do I go about finding out what can I say about Z1, Z2 and Z3? Well, if this is omega Z2, then you must turn this by 120 degrees. And then move this here for you to get Z2. Because this will be Z2. So this will be Z2. So that will be the point. This will be one point. That will be another point. And then this arrow, right, just shift it here. This is omega square Z3. So you must move it again 120 degrees. Either you move it 240 degrees that way, or you rotate it by one more 20 degrees. You will come to where? Z3. Because omega square Z3 is 240 degrees from Z3. So if I turn this by 120, this point will be Z3. I've got Z1, Z2, Z3 lying like this. Okay. So from here, what do I do? That's interesting. Because the magnitudes of these three is not given. I should have added that a little more, but then it would have become very easy. Because then this would be this will be an equilateral triangle. And then Z1, Z2, Z3, I should have given you that information. I've not given you that information. I'm just trying to see what I can do with this. Because, wait. If this is true, then it also means multiply by omega. It also means Z3 plus omega square Z2 plus omega Z1 is 0. It also means, yeah, hold on. So I can do it differently. Geometry was not very helpful, but this is very useful now. Z1 plus omega Z2 plus omega square Z3 is 0. I only made the question, but now I forgot what I did at the time. Multiply by omega Z1 plus omega square Z2 plus omega cube, which is just 1, Z3 is 0. Again multiply omega square Z1. That doesn't help. That doesn't help us. Of course, it will be 0. That is not a point. Because basically I was looking at what I will get. So if I multiply, I'll get this. If I add them, though, I'll get 0 times Z1 plus 0 times Z. That's not helpful. Unfortunately, I have to use this. Okay. There is a small mistake, I think, or at least I have not mentioned it here. If modulus of Z1, modulus of Z2, modulus of Z3 is the same or equal. Okay, so that should have been mentioned, otherwise it's not useful. How is that? Doesn't it make it equilateral triangle? No. Remember, equilateral triangle is Z1 minus Z2. I need Z1 minus Z2. Oh, okay. Hold on. I think I can solve it anyway. So I don't need this. I can solve it anyway. Let's see. Basically, if I add, just give me a second. If I do, just hold a second. Suppose I multiply by omega and I add these two, I'll get omega square. Z1 minus Z2, right? Yeah. Okay, I got it. I should have done that before. The problem is when I'm creating the question, it is easy. After that, I forget what I did. Okay, omega Z2 plus omega square Z3 is 0. But omega square is 1 plus omega with a minus sign. No. So that means if I now join this, I can write Z1 plus omega Z2 minus Z3 minus omega Z3 is 0, which means Z1 minus Z3, okay, is equal to omega times Z3 minus Z2, which means length of Z1 minus Z3 is equal to the length of Z3 minus Z2. What does this tell you? This tells you it's an isosceles triangle. Because Z1 to Z3 and Z3 to Z2, the distances are equal. If this is Z3, this is Z1, this is Z2, the distances are equal. Right? How did I get this? Because if I take modulus here and I take modulus there, what is modulus of omega? Modulus of omega is 1. So therefore, Z1 minus Z3 modulus is Z3 minus Z2 modulus, which means this distance is equal to this distance. So therefore, it must be an isosceles triangle. But Z1 may not be, Z1 minus Z2 may not be equal to this. So we cannot say it's an equilateral triangle unless I figure that out. Wait. Let's check. I might be able to do that also. Hold on. It might be an equilateral triangle because this can be written as 1 plus omega square with a minus sign. So again, if I do this, I'll get Z1 minus Z2. Okay. And then this will be plus omega square or minus omega square. Z2 minus Z3 is 0. Yeah, it is an equilateral triangle. Z1 minus Z2 modulus is modulus of omega square. So Z2 minus Z3. So all three are equal. These two are equal and these two are equal. So it is not just an isosceles triangle. These two are equal. These two are equal. So everything is equal. So this is an equilateral triangle. Okay. I didn't have to give you this information. This was not required. Okay. So it is an equilateral triangle if this is true. Oh yeah, correct. I should have thought of that. Okay, so if I look at a triangle, imagine that I had a center. So I'm going to call it Z0. Let's call this as Z1. Let's call that as Z2. This arrow, this angle is 120 degrees. This angle is 120. If it's an equilateral triangle, this angle is 120. So this is Z1 minus Z0 multiplied by omega gives you this arrow, which is Z2 minus Z0. And Z2 minus Z0 multiplied by omega gives you Z3 minus Z0. If it is an equilateral triangle. Multiplying, turning by 120 degrees is just simply multiplying. It's an equilateral triangle. Z0 is the center or centroid for an equilateral triangle. So this is how I constructed the question, I think. I remember now. Okay. So if I now take everything together, omega Z2, okay, minus Z3 is omega Z0 minus Z0. Okay. Similarly, or actually I can do omega square. I can do omega square. So let me rewrite this as omega square z2. So I'll write it here. Omega square z1 minus z0. Take this and multiply by omega 2 times is z3 minus z0. Right? So if I now add these two up, I'm going to get z2 plus z3. Okay, or better, multiply this by omega and add. So I'll get z3 plus omega, z2 plus omega z3 minus z0 into 1 plus omega is, this becomes 1. So if I look at this, I get z1 into 1 plus omega, z1 into 1 plus omega minus z0 into 1 plus omega. So this will cancel out, giving you only this. But 1 plus omega is minus omega square. So if you take it to that side, you will get z2 plus omega z3 plus omega square z1 is 0. And so if I multiply by omega, I'll get whatever I started out with. So this, I'm just telling you how the question was first framed. I started out with a equilateral triangle. And I showed that this must be true. And if you use this, you can derive that it must be an equilateral triangle. It's a little complicated, I know. Okay, so we should stop with this. We should stop with this question. From the 12th question onwards, we can do it next time. Not right now. Okay. So Usha ma'am, did you
Yes,
do
sir.
did you do
Then
some this thing? Did you ask the poll or shall we continue with differentiation?
Sir, we'll continue with the differentiation, then we'll come back to complex numbers, sir.
Usha ma'am is worried that we won't complete portions. Okay, good. So let us finish. Yeah, let's finish portions. That's better.
Yes, sir.
So, this question is definitely an advanced question, Srivatsan. This won't be a mains question. But in advanced, they usually ask this rotation with omega. So makes it easy. Okay. So the first one is very trivial. First question, second part was quite trivial. The third one, okay, Z1 plus, I think it's a theorem. Z1 plus omega Z2 plus omega square Z3 is 0, means Z1, Z2, Z3 will form an equilateral triangle. I like to show it by using that Z0. So I forgot what I had done when I was trying to derive it. 1 plus omega, Varun Chandar, 1 plus omega square is 0, correct. But Z1 plus Z1, Z2 omega plus Z3 omega square is 0. Doesn't mean that they have to all be equal. No? They are all not the same point. They are not the same point. In fact, magnitude of Z1, magnitude of Z2, magnitude of Z3 may not even be equal. Okay, they don't have to be equal. It is only the triangle formed by them has to be equilateral. There is no common factor. Anirudh, no. Varun, no. That's not correct. Yes, we can also use this. Z1 square plus Z2 square plus Z3 square is Z1, Z2 plus Z2, Z3 plus Z3, Z1 for an equilateral triangle. Okay, you can do that. Not a problem. Anyway, there are many things that we will learn for equilateral triangles. But right now, let us just stop here. Okay, so we will see you next class. We are going to start with differentiation. Okay, I will come back to complex numbers. Limits, complex numbers, we'll keep coming back doing revision. We'll also do other topics like trigonometry, etc. So first, let us get to differentiation. Adinarayan, we will do exponential limits after we start derivatives. Otherwise, we'll take forever to get to derivatives. Okay, with this, we will stop. Thank you. See you next week.